This video will introduce our work, which has been accepted by ECCV 2024, Vectorized HD map construction using geometry. Why construct vectorized HD maps online? Traditional global high-definition maps are constructed offline from large amounts of LiDAR point clouds, which is costly and time-consuming. Online HD map construction, on the other hand, builds local maps from sensor data such as cameras and LiDARs, offering timely and low-cost advantages. Vector maps are an emerging way of utilizing maps, often with higher computational efficiency for downstream tasks. After constructing maps using our method, you can apply them to many areas such as motion prediction, lane occupancy prediction, and planning. In this work, we noticed an overlooked attribute of map instances, geometry properties. Here is an example. When the ego vehicle turns right or moves forward, the shape of the crosswalk remains unchanged. Existing representations are often based on absolute coordinates, which change significantly as the ego vehicle moves, meaning these representations are sensitive to rotations and translations. Here is a real scene where the baseline model predicts a distorted crosswalk shape in this tilted scenario. Moreover, HD maps consist of different types of map instances with various geometry properties. Without distinguishing these differences in geometry properties, a naive point-centric attention mechanism finds it challenging to effectively learn both shape and relation properties, as shown in the figure. We have made improvements to address these issues, and the following video demonstrates the overall performance of our method. In the first clip, raindrops obscure the windshield, causing the baseline model to fail in recovering the occluded road boundary. However, our method avoids this issue. The next part includes two other driving clips with severe rotations or occlusions, where our method still achieves better results. As seen, when the ego vehicle turns left, our method avoids losing the map instances ahead on the right. In this clip, a crosswalk with a complex shape is first obscured by a truck and then by a black car. Our method perceives the shape better under such circumstances. Specifically, we propose additional geometry representations. Let's first focus on points and displacement vectors. We believe that patterns of local clues can reflect the shape of instances or relations between instances. Here, we use the angles between displacement vectors and the distances between points. Combining these local clues at each point of the instances, we obtain geometry representations. In our proposed geometry representation, a rectangular instance with 4 vertices can be represented by one 90-degree angle and 2 pairs of equal sides. Similarly, a straight line can be represented as all angles being 0 degrees or 180 degrees. Additionally, we distinguish two different types of geometry properties, the shape of a single instance, e.g., rectangles, lines, etc., and the relation between different instances, including parallel, perpendicular, specific lane widths, etc. Due to the relative nature of angles and distances, our geometry representation remains invariant under rotation and translation. Based on this geometry representation, we propose the GeMap method. GeMap consists of two Euclidean loss functions. One is the shape loss and the other is the relation loss. To optimize the geometry representation, we calculate the model's prediction and the label's geometry representation separately and define the corresponding loss as the L1 norm distance between them. Additionally, due to the existence of two different geometry properties, shape and relation, we also adjust the attention module to form geometry decoupled attention. We use shape attention between points within a single instance and relation attention between points of different instances. Decoupling these two types of attention facilitates learning various geometry properties. GeMap achieves the best results on the NuScenes dataset. With additional LiDAR input, GeMap can also enjoy further improvement. GeMap also shows extraordinary performance on the Argoverse 2 dataset. What can be done based on GeMap? First, you can prepare your own map dataset and use our proposed GeMap method. Using GeMap in the detection 3D framework is very simple, just download the source code and set the config. Second, to enable the model with longer-range perception capabilities, considering temporal fusion and multisensor fusion based on GeMap is also a valuable direction. Finally, geometry properties are actually widespread in autonomous driving tasks. For example, vehicles in the same lane often have similar orientations. Therefore, the idea of GeMap might also be transferable to other fields such as object detection and motion prediction. Thanks for your listening.